Okay, happy Friday, everybody. Hope you're cooling down in this nice Arctic air conditioning, right? So obviously the most important thing for next week is the lab test. I hope you've been getting familiar with the questions. Now, just if anybody has lost a book, this looks like, I'm not sure whose this is. I don't think there's a name. But, yeah, there's no name. But I was looking through it, and I don't know, are these smiley faces or are they arrows? You think they're arrows? I think, you know, yeah, they could be both, right? I might use that in something. I think that's pretty cool, right? Anyway, hello to everybody at home. We've got 7 people online at home. Let's see. Oh, now there's 9. So in today's class, I thought we could do 2 things. The first thing I thought we could do is just do a little bit on differential equations, and then the rest of it we'll spend on lab test 1 prep. Is that okay? Yeah. All right. So I won't spend too long on this, but I like to be ahead in the lectures if I can be. But before I get to that, I just wanted to add something to this slide. This is page 67 from the notes. Earlier this week, I think I introduced these first moments, right? And I brought them up as sort of an expansion or a generalization of these centroids and center of masses and things like this, right? And I wrote down the general forms of the first moments, but I didn't label them, okay? So in Mobius, in week 5 or week 6, you'll get questions on this, right? And so the way I remember it, basically for this first moment, this is the first moment about the y-axis. So basically it's the distance to the y-axis, which is x, times the mass or the or however you want to think about that second bit, okay? And it's the same with the other first moment, right? So if you, this one's about the x-axis. So, you know, if you have a point, say, here, and here's the x-axis, here's the y-axis, obviously the distance from that point to that axis is y, okay? And the distance from that point to that axis is x. So in the simplest terms, I try to think about these as distance times mass, okay? And double integrals allows us to compute these first moments about the axes of all sorts of different 2-dimensional shapes. So that's something you'll see in Mobius coming up, okay? Okay. All right, so this section, like many of these sections, is very overlapping with stuff you already know. Oh, it's okay. That's fine. Come on in. No problem. So where do you see ordinary differential equations in first year math courses here? Can anyone remember? Anyone? Where do you see them? Where have you seen them in the math courses?
In Math 1B.
Yeah.
In Math 1B.
Yeah. Exactly. There's like a whole topic on them. Yep. And you do first order, second order. So the basic starting point here is this, okay? And I think you'll actually be very surprised that some of the stuff, a lot of the stuff that we see has already been covered in these first year courses, okay? It doesn't mean we won't learn anything new, but the stuff is really covered in those courses. So let's refresh our memory and we can talk about it, okay? So, what is an ordinary differential equation? Well, I'm glad you asked, okay? I'm glad you asked. So, hang on, where did you go? Aha. So, ODE. Now, ordinary differential equations have two things. Okay, at a super basic level, there are two things in an ODE. Can anyone tell me or guess what they are? There are two things, at least two things. Anyone? What are they? What's one thing? What's something that every equation has? It's not a trick question. Oh, yeah.
An equals?
Yeah, it has an equal sign, right? It can't be an equation if it doesn't have an equal sign, okay? So that's that bit. An equal sign. And what else? A derivative. That's it. Okay? So it's an equation with a derivative in it. Okay? Like most equations, you want to solve them, you want to understand them, you want to find stuff out. Okay? So let's look at an example. Here's an example. Here is an example of differential equation. Okay, so look at the bottom one first because that's a bit more specific. You've got a derivative, you've got an equal sign and something else. Okay? If you think back to 1231, Math 1B, part of the challenge in solving these problems was all about classifying. Classifying, oh, is it this type of equation? Is it this type? Is it this type? And then you apply a technique, okay? So for these special forms, we give them a special name, okay? And the very first one that you look at in Math 1B is called a separable differential equation, okay? So it can be, a function of x times a function of y, or it can be a function of x divided by a function of y, something like that, okay? The most important thing is that the variables are separated by multiplication or division, okay? So can anyone remember how to solve a problem like this? What do we do? Think back to first year, that glorious year of discovery. Any ideas?
Is it like split your dy dx, so you get like dy on one side and dx on the other, and then put all your variables accordingly?
Mm-hmm. Yep. So the way that I remember, it's exactly right. The way that I remember how to do it is basically you separate the variables, right? So the x's and the y's, and then you integrate. So you separate and you integrate. Okay? So if you look here, right, we're looking for a solution like that. Let's bring the 2y up here and bring the dx up here. Okay? Now you might think, well, what the hell, how did you do that? How can you just split up a derivative? Well, Derivatives are, strictly speaking, not fractions, but you can kind of treat them like fractions. Okay? So it's not quite sure what's going on here, but I have separated, would you agree I've separated the variables? There's y's on one side, there's x's on the other, and now if I integrate it, suddenly gives a bit more meaning. So it's a two-step process. You separate. And then you integrate. Okay? So now it makes a bit more sense. Would you agree? Now, a good question here still is, why can I do that? Okay, we'll talk about that in a minute. But let's just actually solve the problem and try to solve for y. So if I integrate the left-hand side, what am I going to get? Yeah, y squared. On the right-hand side, like a negative half x squared, something like that. And so let's continue down here. Don't forget the constant of integration, because there's something that we would like to know. So, believe it or not, this is what you call an implicit representation of the solution y. Okay, we don't know what c is. Maybe we can rearrange it and get y, but that form's fine. Okay, but let's look at the constant of integration for a second. If I slightly move that to the other side, I get, so that comes to that side, I get that. What can you tell me about the sign of c? That constant, we don't know what it is, but can we say something about its sign? Yeah, it's positive. It can't, well, I guess it can't be zero. It can't be negative, right? So it's greater than or equal to 0, because it's a sum of squares. Okay? So all right, so part B, if we have extra information y of 0 equals 1, that's called an initial condition. So it tells you a little bit of data at a point. In this case, the value of the solution's 1 when x equals 0. Okay? We can use that to compute this constant c and solve, like sort of simplify this a bit more. Okay? Bless you. So let's try. So if that's our initial data, then I'm going to go to my general solution, sub in x equals 1, sub in y equals 1, and try to find c. Okay? So this is going to become something like 1 squared plus a half times 0 squared equals c. So what's c going to be? 1. Okay? So let's write out our solution here. Okay, that looks okay so far, but let's see if we can get y. Let's see if we can get y. So let's simplify a little bit and try to make y the subject. Okay. So now it looks a bit weird because it looks like we've got two solutions. Right? It looks like we've got two solutions. But let's go into, let's actually draw those two curves. See what they look like. Okay. All right, so the top curve is the positive square root function, and the bottom curve is this blue, the negative square root function. Now, one of them we can ignore. Can anyone tell me why we can ignore sort of one, the green or the blue part?
The initial condition was positive, so we're just going to take the positive.
Exactly, right? If we go back to our data, our initial data, the solution has to pass through 1 at x equals 0, right? So I'm just, so for everyone at home, if we just go back to our data, when x equals 1, the solution has to be positive, right? It's 1. So if we go to our graph, it has to go through that point, right? It can't go through that point. So that's our solution, okay? Now, note that it's only defined for x values between, you know, like something positive and something negative. It doesn't go for the whole of the x values. That's okay, all right? So with these problems, and you will see problems like this, sometimes there's a little bit of work in finishing off the problem and simplifying, okay? So as a sort of conclusion, that would be our conclusion. Now, how do we know if we're right or not? How can we test this? Well, you can take this, you can differentiate it, and then plug it in here. If the left-hand side and the right-hand side are the same, then it's a solution to the given equation. Questions? Are you having flashbacks to Math 1B? Yeah, am I right? Okay, so that's separable equations. So the main test, or the main trigger, if you like, is to look for multiplication or division between the variables. And then you can separate them, you can integrate. Okay, I'm so fixed on working on my German accent that I can't spell. Okay, so separate, integrate, simplify. Questions? Separable equations are sort of the entry level type of problem, but they can get quite difficult. They can get quite difficult, especially when you're going from some sort of implicit form down to something a bit more definite. It doesn't always work out, and sometimes you can get more than one solution, right? That's still okay sometimes. In physical problems, you would expect one solution though, okay? Does anybody know why? Why in sort of a physical problem would you expect one solution? So, you know, you're modelling something, you've got your ODE or whatever, your initial value problem, your initial conditions. Why would you hope for one solution?
Because usually something physical can't be two things at once.
Yep. Exactly, right? It sort of, it doesn't agree with physical reality, right? And also, if you repeat an experiment, you would hope, right? Oh, this is when I need like a ball or something. Anyone got a ball? Anyone? Okay, this will do, right? If I push this chair, right, and I push it again with exactly the same force, it's going to do the same thing. Right? It's not going to go over there. right? So you would hope that when you did experiments, they were repeatable, at least simple ones. It's the same with the solutions to ODEs. You wouldn't want more than one because it's not particularly useful or reflective of reality. Unless you're doing, yeah, here we go. Someone had to weigh in. Unless you're doing quantum stuff. Yes, so I'm talking about deterministic models, right? We're not talking about all that other stuff. Anyone doing computing here? Anyone interested in computing? I keep hearing about quantum computers. Where are they? Yeah, are they? I don't know. I've been walking past that building for 20 years. Where's my quantum computer? Come on, Michelle. Come on, I want my quantum computer.
Go in two places at once.
Oh, very good. I like it. Yeah. So anyway, so for our purposes, we'll restrict ourselves to simple deterministic models. Okay. Let's just have a look at another one quickly. Let's have a look at this one. Right, this is the method. Let me just put that on for everyone at home. Right, so to solve a separable ODE, you separate the integrals by division or multiplication, and then you integrate, then you simplify. Okay? The standard method is always the same. Now, does anybody know? Okay, so hang on, before I do this one, let me just hold up. Let me just hold up for a second. Who can justify going from here to here? Does anybody know mathematically why it works? It seems nice, hey, just rip stuff apart, throw an integral sign in there, it's all good. Does anybody know what's going on behind the scenes? Anyone? It's simpler than you think. It's simpler than you think. Anyone? Anyone want to guess? Yes.
Is it just multiplying each side by the lower half?
You're kind of on the right track. You're on the right track. I'll give you a hint. Yes, it's multiplication. It's got something to do with multiplying derivatives. Oh, who said that? Is that what you're going to say?
Yeah.
Oh, say it.
Is it chain rule?
Yeah. It's just the chain rule. Okay? It's just the chain rule. So if you want to know why that works, it's just the chain rule. Okay? Which is something that most people see at school. So using these basic ideas, you can solve these differential equations. Let me do one more, and then we can maybe switch over to some revision. Okay. Let's look at this one. B. Okay, this is another differential equation, and you have some extra information, some extra data. So collectively, we would call that an initial value problem. Okay? Or IVP, initial value problem. Okay? All right. So, is it separable? Yes. Is it separable? Yes, it is. Why? Because it's the product, the right-hand side is the product of two things involving x and y. Okay? So, let's solve it and see what we can do. Okay, so separate the variables and integrate. I'll solve this general case first, and then I'll manage the y of 0 equals 1 later. Okay? Now, what are we assuming when we divide by y? Can anyone tell me? It's non-zero. Okay, is that okay? All right, well, let's do a sense check. Let's do a sense check for the solution y equals 0. If I differentiate 0, what do I get? 0. And if I multiply by 0, what do I get? 0. So 0 is a solution to that, but it doesn't satisfy that condition. So I'm okay. I'm okay. 0 is not a solution to the general IVP. Okay? Just a little bit of housekeeping. Okay, so let's integrate this. Obviously, the right-hand side is going to go to something like x squared, and the left-hand side is going to go to something like natural logarithm. Okay? Now, we don't know whether y is positive or negative. So, to keep things safe, I'm going to put in the absolute value when I do the integral. Okay? So what I'm going to try to do now is get the y out, make it the subject, y equals something. Okay? So who can tell me what undoes the natural log function? What's the opposite of it? Exponential. Okay? So maybe I can do this, guys. Yep. So from there we go there. Okay? So let's take the exponentials of both sides. Okay, so I've taken exponential on the left-hand side and the right-hand side. I get something like this. So I'm on the right track because I've almost got the y on its own, but I've just got to manage this absolute value sign. Okay? All right, so let's write it like that. So that's just the exponent laws. Okay? Now, let me introduce you to a magic constant. Okay? A magic constant. Right? If I get rid of this absolute value of y, then what happens? I get something like that. Right? Now, this magic constant is going to cover three cases. Positive e to the c, negative e to the c, and 0. Okay, it's a magic constant. Okay? So putting that A in there makes things a little bit simpler on the eye and on the brain, and it serves its purpose. Yes?
How does the e to the c become 0, though?
Because, okay, yeah. So, because, it goes back to what I said earlier. Technically speaking, if we forget about that, y is still a solution. Y equals 0 is still a solution. Okay, so I'm just covering all the bases. Yeah, like we know it won't be because of that, but at the moment we haven't used that initial condition at all. So you're right. So again, magic constant. Okay, all right, it's a good question. All right, so now we want to find this a, whatever it is. So let's consider, please. All right, so let's go up here. Let me make that a bit clearer. Okay, we're going to put in x equals 0, and we're going to set the whole thing equals to 1. Okay, so you can see here, a is going to be 0. A is going to be 1, sorry. All right, so let's take that, put it in there, and we'll get our final solution. Boom. Okay? So, that's another example of this separate and integrate stuff. And it's not hard to do that, but when you're sort of doing the last bit of algebra or whatever it is, it can get a little bit annoying. Okay? Questions? Yes.
How do we know y can't be 0 based on y 0 equals 1?
Oh, well, because, okay, good question. Because if y is 0 everywhere, it can't be 1. But it's saying when x equals 0, it's got a value of 1. So it can't, unless we live in this quantum world, it can't be 0 and 1 at the same point. Would you agree? So let's draw a picture. Yes, y equals 0 is a solution. That's the 0, right? Y equals 0 in the plane. But at this point, it's 1. So how can it be 0 and 1 at the same point? It can't, right? Because it goes like that. Right? It's just a horizontal graph. But the initial condition is saying at x equals 0, it's 1. It's not 0. Can't do it. Okay? Can't do it. Why is a equals 0 a solution? Okay. Why is a equals 0 a solution? Well, I'm not saying it's a solution to the general problem, but when a equals 0, y equals 0, and y equals 0 solves this original problem. Not that, but that. Okay? So it's just a bit of housekeeping to make sure they're like Pokemon, right? You've got to catch them all. Okay? So you got to, just when you're doing the first bit, you've got to catch all the solutions. And then the extra initial data gives you something specific. Okay? So in the language of Math 1B, Math 1231, you would call this form the general solution. And then this form a particular solution. Okay? All right. Shall we do some revision? Yeah. No, you don't want to? You asked me a question though. Did you ask me a question last time about Lagrange? I think you did. I was working all night on this solution to find the best one. Yeah.
No, I don't
Yeah.
want this. No, this is trick. I don't want
No,
it to
it's,
go.
well,
Because they do y and then for y and then you get your lambda and then you put your lambda into x, y and then you get something of x squared equals something y squared and then x squared something y squared and then solve. I think that's the easiest I can find.
yeah, I think that's my conclusion as well. So I'll show you what I got and let's see if you got the same. Okay? So let's do some revision. Okay, so I think this is the one, right? This is the question, yeah. I think this is probably the most triggering question in the whole test, right? Let me know what you think. Let me know what you think. Because, the stress, the anxiety with solving this is not, it's not nothing, right? It's not nothing. So when you talk to me about this and said, look, here's my solution, do you have a better one? I thought about it and I'm thinking, I'll try to give you my best solution, okay? Maybe there's a better solution. If somebody knows a better way, let me know. Okay, so let's read the question. You've got a temperature function. So for any point in three-dimensional space, you've got a temperature associated with that position or that point. And then you've got a surface, right? So here the thing you want to maximize, the highest temperature, is the T function, and the constraint will be in the second line, right? So the way I usually think of this, I think of it like this. So, yep. Oh, have I got it? Yeah. Okay. So this is basically going to be g minus 6 equals 0, where g's that mess there. And this is the sort of the system of equation, the system of equations that I want to work on. Yep, subject to no, actually, let me change that because I don't like that. Okay, that's a bit better. Okay, so I've got this, and they're basically my equations. So let's start with the gradient equations first. They basically say at the points of interest that the normal vector, the two vectors grad t and grad g are parallel. Okay. So how did I do it? Well, let's do the differentiation. So remember, the del operator is just defined like this, and you apply it to t, so you're going to get something like this. On the left-hand side, it's going to be dt dx, and then dt dy, dt dz, and there's your function. So the first one is going to be that. The second one's going to be something like either y is going to go to 1, so x cubed y squared, z squared. And the last one with respect to z is going to be 2, and then that's going to become z. Okay, and then on the right, okay, grad g, it's going to become 4x, and then 4y, and then 2z. 2z, yeah. Okay, so that's the sort of entry step. You got 3 examples, 3 equations, and you got g equals 0. Okay, so the way I'm going to solve this is basically by isolating the lambda. Okay, so if I do that, watch what happens. So just divide that by 4x. Okay, and I can simplify that. The x is going to cancel out, assuming x isn't 0. Okay, for the second one, I'm going to take the 4y over there. And for the third one, I'm going to take the 2z over there. So I can simplify that. Okay, you can knock off the 2z's, again assuming z's not 0. Okay. So now you're sort of faced with a challenge of how to solve these equations. Okay, so I'm looking at these very carefully now, and I'm trying to look for patterns between the equations. Okay, so there's a couple of things that I can see. Maybe you can see other things, but the first thing I see is that there's a z squared there and a z squared there. Okay? So if I let equation 1 and equation 2 equal each other, because they're both equal to lambda, those z squareds will disappear. And then I'll just be left with x's and y's. So I'm already trying to think about how to simplify it. Is this looking familiar? Yeah. Okay. So that's the first thing I notice. And then what do you notice here? There's an x cubed and an x cubed. So if I set equation 2 and equation 3 equal to each other, the x cubes are going to disappear and I'm only going to be left with y's and z's. That's all you need, right? That's all you need. So let's do that and work through it. So 1 and 2. So we set them equal to each other. The z squareds are going to disappear. The 4 is going to disappear and x is going to disappear, right? So that's a good place to be. So let's I don't know, I can rearrange this and say x equals plus or minus the square root of y, something like that. Square root of 3 times y. So that's some information. Great. Okay, now let's work with equations 2 and 3 because they share a common bit in the x cubes. So let's let them equal each other and see what happens. Okay, so the x cubes are going to cancel each other out and we're going to be left with something like, well, I'll just write it down, hang on. Okay, so bam, bam. Bring the 4 up there. So z squared equals 4y squared. Okay? So you see now, I've got x in terms of y, z in terms of y. What haven't I used yet? I haven't used my constraint equation. I haven't used this surface, this g equals 0. And notice every term has a squared in it. So if I know x squared in terms, y squared in terms of x squared, z squared in terms of y squared, I can substitute these things in and get something in terms of one variable. Okay? So that's the idea. That's the idea. All right? Okay, so we've got so let's replace x with x squared with that, z squared with that, and I'll get something in terms of y. Okay? Okay, so we're going to get 12 y squared equals 6. Holy moly, we've done it. Let's get the values for y from that. So y is going to be plus or minus 1 on root 2. Great. Okay, so now we can go back to our earlier working and find x and z values from the boxes. Okay, so if y equals positive 1 on root 2, x is going to be positive root 3 times 1 on root 2. If x is negative 1 on root 2, y is negative 1 on root 2, x is going to be negative root 3 times 1 on root 2. Okay, so we're going to back substitute. Okay, now you can simplify these. Oh, hang on. That should be our root 2 down there. Okay, so there are our points of interest. So do we want the positives, the negatives? What do we want? Well, let's go back to our temperature function. Let's go back, way back. There's our temperature function. Okay? So if x, y, and z are all positive, you're going to get a positive answer. If x is negative and y is negative, doesn't matter what z is, you're going to get the same answer. Okay? So you don't have to test all these points. You can if you want to, but you could just choose all the positive values. Okay, so you put those into there, you'll get a bit of a mess, but here's what you get. Again, you don't have to simplify this because Mobius does it for you. Okay? Now, I did try, so is that looks familiar to you? Yeah? Hang on. Yeah, no, you got to contribute. Come on.
I'm not really good with like surd, right? So let's say you see y squared equals 6 over 12, then you get half, and then you sub half times 3, and then half times 4, you get 3 over 2 and 2. Then it's easier to type than...
Yeah, exactly. Exactly. So when you're typing into the answer box in Mobius, of course it's easier to type simple stuff and shorter stuff, right? I get it. Now, I'm not sure who uses artificial intelligence here every now and again? Can I have a show of hands? It's okay, you're not in trouble. No, I do, all the time. Almost every day I do, right? So I put this problem into ChatGPT. Right, just the standard version. What do you think ChatGPT said? Do you think it could do it? Yes. It could do everything except, and it comes back to your question, the last line. Do you know what it said? It said, I'll show you later. Oh, the answer is 6 root 6. So of course, what did I put into Maple? Wow, ChatGPT, you did me wrong. So it could do all the hard stuff, but actually the surd simplification, it didn't like it. Why? Hang on. Tell me.
Because if you do ChatGPT, right, and then they would go y squared, they will leave it y and then root 2. That's what they did on ChatGPT. They don't do whole thing, square root of whole thing. Well, that's why the answer is...
Well, ChatGPT is quite funny because as soon as I knew it wasn't right, I'm like, you've made a mistake. And it's very obedient, it's very gracious. It's like, oh yes, I have made a mistake. Thank you for pointing that out, right? Yeah, and then on the second attempt, it got the right answer. So it took a while to get it. Yeah, so I think that's the quickest and easiest way to solve that sort of problem. Does anybody know an easier way? A quicker way? Let's get there. What was it? The comment the other day was Tisdell flexing his bands, something I also had to look up on the internet, right? Yeah. So I'm thinking about running a competition to see who can come up with the best solutions to problems, right? So if that's something you're interested in, let me know. Instead of training ChatGPT, you'd be training me, right? Let me know if you're interested in that. People at home, what do you reckon? Should I offer a prize for the most creative solution to some problem? I would be interested in that. Let me know what you're thinking at home. Here we go. The debate's on. Copilot is better for maths. Try Copilot. I've tried Copilot. It is the UNSW endorsed GAI. Do you know this? Yeah. I would say for me, it's not very good. But maybe there's other ways to use it that I'm not aware of. Okay? So, hang on. So yeah, so try Copilot, definitely. All right, let's take a 10-minute break. We will come back with more after the break. Just something, so let me show you the conversation I had with ChatGPT, right? So I was just curious to see if it would give me a faster solution or whatever, right? So I just typed it in and it starts off, let's solve this step by step, blah, 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 you know. Anyway, it keeps going. And then it comes up with the final answer, 6 root 6. And, you know, my calculations didn't give that. And Mobius also said that it was wrong. So I was a bit cheeky here. I said, is 6 root 6 the same as the correct answer? Right? And let's carefully compare them. Right? Blah, 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 blah. They are not the same. So then I said, I think your answer for the highest temperature is incorrect. I was quite nice about it. It should be this. You made a mistake. You know, in this modern sensitive world, you're not allowed to say people have made mistakes, but you can say it to ChatGPT probably. You made a mistake in the very last line of your working. You're absolutely right. I made a mistake. Let's fix that. Okay? So, and then it goes, it's confessing now, I mistakenly wrote that before. That was wrong. Thanks for catching the mistake. Good eye. No worries. So are we training the robots to take over? I don't know.
You should give it the answer because half the time it'll just do the calculations again and then just put your answer at the bottom.
Yeah, exactly. It's got a finishing point and so it'll somehow get there. Yeah.
Like, no, do the wrong calculations again and just put
All right. So let's have a look at some more questions. This is from the practice test. So this is divergence. Okay. So divergence is one of the operators, one of the operations, I guess, from vector calculus. And remember, when we have the dot there, we basically take the derivative of our vector field, add them all together, and we get either a number or an expression that's not a vector. Okay? So the first part of the question is a computational one. And the second one's a bit more conceptual. And in fact, I think somebody posted in the Moodle forum about part B. Okay, it was either 2019 or 2018, I can't remember. But part B is probably a bit more exciting. Okay, so just let me look something up because I wanted to show you a web page. So let's look at the bottom one for a second. Because, you know, sometimes I'll just ask the interweb what's going on, right? How good is Reddit? So why is the divergence of the curl, that's part B, always 0? Now you can prove it, you know, all that sort of stuff. But I'm just interested to see people's answers for this. Because people, you know, they'll offer answers, right? And so this person goes, that's too long. But coffee and maths is hitting it. Okay. Curl measures how swirly there is, and divergence measures how much boom there is. And everybody knows that swirly and boom are tangential to each other. That's pretty much right. Yeah, that's pretty much right. So, you know, if you look at the expression again in part B, right, this is rotation and this is boom, right? You know, of course they're going to be zero, right? You can't have an expansion of a rotating field. I mean, if you can find me an example of that, I'd be pretty interested. Okay? So you actually don't need to work out part B. Part B works for anything as long as the mixed partial derivatives are equal. Okay? If ChatGPT knows it made a mistake, then why did it make it? Yeah, I think ChatGPT is a bit of a, I don't know, like, what's a good word for it? It's a bit of a simp. It's a bit of a simp, right? Would you agree? I would say ChatGPT is a bit of a simp because you tell it something, it goes, oh yes, you're absolutely right. You know, it's like 1 + 1 = 3. Oh yes, thank you for helping me, right? Like, is anybody learning languages here? Anyone learning a language? Right? So I will chat to ChatGPT on my phone. I'll have conversations. You know, how was your weekend? Whatever in German or whatever. And it's so funny, right? It is like you're having a conversation with a simp. And you know, oh, you speak so well. And it's like terrible, right? Like, oh, you speak really well. Your accent's great. And I'm like, no, it's not. It's terrible. Don't tell me that. What you need is like a taskmaster ChatGPT who just tells it like it is. Okay, back to the program. Sorry, I'm going a bit off topic today. All right, so let's look at the divergence first. So, okay, sorry, back to the program. Let's look at the divergence first. So, ddx of the first component plus ddy of the second component plus ddz of the third component. So, let's do it. So, we want to differentiate that with respect to x, right? And then that component, differentiate that component with respect to y. And the final component with respect to z. Okay, so if you know your partial derivatives, you can do this pretty quickly. Just need to be careful you don't make a silly mistake. So it's going to be 5x to the 4 times y to the 4. That's going to be 0. Cos is going to go to negative sign, and the z is going to come to the front. And then it's going to be the same for this one. Now, like you were saying before, what's the risk here? The risk is you type that in and you make some sort of syntax error. Yeah? So how did I do is the key. Yeah? People were arguing with me though on Moodle. Like they put the wrong syntax in and they're like, oh, what? Like, why isn't my preview working? And it's because you got the wrong syntax. And then they're saying, oh, could I argue that this is correct? I'm like, no. Like you can check the syntax, right? You can check it. All right. So the divergence of the curl is always 0. Okay? Now there's two ways that I can justify that besides the boomy swirly thing from Reddit. Okay, boomy and swirly are tangential. Okay, let me give you the really easy Math 1A explanation. Okay, and I actually like this one better. No disrespect to Reddit, Reddit's cool, but remember, oh, it's terrible. Oh, let me try that again, hang on. Yeah, that's better. Okay, you've got what's called a parallel piped or a parallel piped. Okay, and you've got three vectors. One vector there, one vector there, and one vector there. Okay, so basically three edges are spanned by three different vectors. Okay, getting flashbacks to Math 1A. All right? And let's say this is vector A, that's vector B, and that's vector C. Okay? Can anyone remember the way of computing the volume of the parallel piped with vectors? Yeah.
Dot cross product.
Yeah. So we would call that the scalar triple product. So you got the dot and the cross. Yeah. So the volume of this mess Yep. So it's absolute value because you want volume. Okay. So what happens if I did this? If I wanted to compute that, or even that. Who can justify why that's 0? The bottom one, this one here. So my question to everybody here, and everyone online, scalar triple product is right. Why is that expression always 0? Based on the picture, or some other reason?
There's no volume. A cross C is basically the area, and then you're just, the dot product doesn't give you any dimension after that.
Yeah. So it's basically you're calculating the volume of a box that has no height. Okay? You're calculating, so in the original thing, the box has definitely got a height, or a width, or a length. But here, basically, you've got two vectors A that lie in the same plane. Okay? So you're basically trying to compute three-dimensional volume from a two-dimensional shape. That doesn't work. Okay? So what does this mean for swirls and curls and booms? Oh my God. It's the same. Oh. Yeah. It's the same. So that's actually how I think of it. I think about it in terms of volume and first year. Right? If you double the operator, you just get 0. And you can think of it roughly as having a box with no volume. Right? Okay. Another way to justify it. Let's do, let's just do it generally, right? So let's say F is this. Yep. Okay, so little f, little g, and little h are functions of x, y, and z. Let's just compute the divergence of the curl of that, okay, and see what happens. Okay, so you can do it like this. So think of scalar triple product. Okay? So you're getting flashbacks to the scalar triple product, hopefully, from first year. So it's that. Okay, so what do we do with these kind of expansions? I start on the top row and I work my way along the top row, right? So it's d dx of the determinant that you can see, minus d dy of the determinant you can see, plus d dz of the determinant you can see. Okay? So if you run through that, what are we going to get? Well, d dx of h sub y minus g sub z. Okay, the subscripts are the derivatives, just to save a bit of space. Okay, that on that minus that on that. Okay, that on that minus that on that. Okay, so it looks like a mess, but when you expand it, you're going to get all these mixed partials and they're all going to cancel out. Okay? So in the first one, you're going to get hyx minus g zx. Here you're going to get hxy minus fzy. Here you're going to get gxz minus fyz. So if you look carefully, boom, boom, swirly, swirly, boom, boom. Okay, assuming that the partial derivatives are, the mixed partials are equal, which is a fundamental assumption that we use in this course. Okay? So that's the long way to do it. You shouldn't have to do it. Just remember the swirls and the booms are tangential, so the dot product's 0. All right? There it is. Okay? Questions? Yeah. Oh. Here's a good question. This is a philosophical question. What to do if ChatGPT tells you that you are wrong? This will happen occasionally. Yeah? Any suggestions? Bless you.
You gaslight it.
Well, that not a bad idea. Not a bad idea. You can wind it up. Absolutely. You know, I was thinking you could say, well, you know, yeah, you could say Copilot told me this, or you know, DeepSeek. Yeah, exactly. Or what was the CCP one? Ask Eric. Ask Eric told me this, right? Yeah. Well, if ChatGPT tells you wrong, I don't know. I mean, one thing that we're talking about at the moment, by the way, in the School of Maths, is the use of GAI, okay? And we're almost thinking about, one suggestion was this. Just give students a printout like this and ask them if it's valid. Ask them if the solution's valid, or how could it be improved, right? And I think that's actually where we're going to a large degree, right? We use Maple, we use, I don't know, Python, we use calculators, we use all sorts of stuff, right? Maps, we use all sorts of stuff. But it's up to us to really think about it and go, well, is this reasonable? Is this interesting? Is this correct, right? So I think that's up to you. If ChatGPT tells you they're wrong, well, maybe you are wrong. Maybe you are wrong. So gaslighting takes effort. So yeah, gaslighting takes effort. It does. Just get Copilot to write the lines for you. I don't know. All right, questions for that one? I've done a lot, and you don't have to do that. But if you remember the swirlies and the booms, you just put in 0. Okay? All right. Let's do another one. Aha. Okay. Right, here's another one. Here's a vector field. Calculate the first component of the curl. Okay, so when I saw this question, I'm like, they have to calculate the curl. That sucks. No, you only need one component of the curl vector. Okay? You only need one component. So I kind of stopped thinking about it after I got the first component. Okay? And then in the second part, part B says if phi is a scalar field, so a function, right? Enter the curl of the gradient. Now, the first question is, well, where's phi? Where's phi? They don't tell you what phi is. So that kind of gives you a hint that there must only be really one answer for all, suitable phi. Okay? So the answer is going to be a vector, but it's going to be the zero vector actually. But let's do the first one and see how we go. All right, so I'll come back to B in a second. All right, so here's our curl. Can I keep it in there? Yeah. And then you've got the components. Can I squish them in? Not really. Okay, I've sort of squished them as best as I can. Okay, so they only want the first component of the curl. Okay, so this question is pretty easy. Yeah, so to get the first component, you start up here, and then you move to the right. So you cover up the column and the row that i's in, and you multiply I by the determinant of what's left. Okay, so it'll be I times all of d dy of this shine term minus d dz of the cos term. Okay? So d dy of that, so what does shine go to when you differentiate it? Cosh. And the 2 is going to come to the front. Minus d dz of that. So cos is going to negative sign, 2z is going to come to the front. Okay, I don't care about the rest of it. Minus. If you do it as a determinant, it's minus. Because it goes positive I, negative j, positive k. But if you feel better, you could put a plus sign there. It doesn't matter. Yep.
Should be 2z y squared.
Oh! ChatGPT, you let me down. All right. All right, let's take that again. So, because that's a constant, isn't it? Yeah. A magic y squared. Thank you. You've made my day. So, assuming you can get it right, the next risk is the syntax, okay? Because that's a mess to type in, okay? All right, so let's look at part B. Yeah, someone at home. You rule. Zach's also on the case. Thank you, Zach. Okay, so let's look at the last one. The curl of the gradient as a column vector. Okay, remember when you compute the curl, it's a vector or a vector field, right? So let's just actually see what's up with that. You don't know what phi is, okay? So it'll be any good class of scalar fields, right? Any sort of functions. So let's write it out. So if I'm taking the gradient, the curl of the gradient, so gradient is just this, where the subscripts are partial derivatives, and so let's do the cross with that. So okay, so now same sort of deal, start up the top and expand along the top row. So what are we going to get? We're going to get, on the first one, d dy of that minus d dz of that. What's that going to give me? 0. Okay, why? Because we can mix the partial derivatives. So that on that minus that on that is going to give 0. Okay, the next one. That on that minus that on that, 0. Plus that on that minus that on that is 0. Okay? May I want to ma? No? May I want to? Okay, so the trigger there for me is they don't tell you what phi is. Okay, so it has to work for all, like a very large class of these phi functions. So I think that's pretty easy marks. Now you don't have to write any of that down. You just write down the 0 vector in the syntax. Okay? You don't have to write down any of that. But that's just why it's true. All right. Let me continue this revision odyssey. Oh. Okay, all right. Now, this is what I'm talking about. Bring out the money again. Okay. So I think I solved this one in a different lecture, but and I've just got like my scribbly notes on the page. But I want to put it to you that there's a way. So when you see this, you think Lagrange multipliers, right? But can anyone think of another way of solving this? So you've got a plane, and you want to find the closest point on that plane to the point 221. Hang on. See, the money gets the hands up, right?
Projections.
Oh yeah. Is that what you're going to say? Yeah. Yeah. Okay. So, where did we learn projections in first year maths? Math 1A, vectors, right? Vectors. So, you get a question like this, you could do it the Lagrangian way, right? Or you just do it using vectors. Okay? There's nothing new there at all. It's exactly the projection that you learn in Math 1131. Okay? And how did I work that out? Well, I'm like, I think I've seen this question somewhere before. You know that feeling of deja vu that you get? I think I've seen this somewhere before. Yeah? So, so I drew a picture and I'm like, holy moly, I'm getting flashback vibes to, teaching first year maths. So there's the plane, there's a point. You want Q to find that distance. You choose A to be on the plane, so you just find an X, Y, and Z that makes that work. And then you just draw a picture. Normal vector is from the coefficients 3, 1, negative 1. Okay? And then you can work out OQ if you know the vector QP. Okay? And it only asks you for the x component of it in the question, right? The exact value of the first component. So I only computed that. I couldn't be bothered doing the rest. Okay? So what I'm trying to tell you here is because we don't give you working out marks. You don't get any marks for working out, right? You can use any method that you like. Okay? If you want to use first year maths to do this, you should be able to do it. If you want to use Lagrange multipliers, you should be able to do that. Okay? So I'm trying to make sure you got options. You got options. Does this bring you back any memories? Projection? Nightmares? Okay? So I thought that was kind of cool. That's an n, but is it? No, that's, what is that? Oh, 1 on root 11. Yeah. Okay. So you can see the answer is the same here as it is here. Okay, they're both written poorly, but they're the same. I just picked it. So the question is, how did I choose the point A? Well, I wanted to find a point A on the plane, and it doesn't matter which one. And so I just went up there and said, okay, what is an easy value of x, y, and z that gives you 4? So 1, 1, 0. There are other ones. Yeah. Okay, just give me a moment. Okay. I think I showed this to you before, but I'm going to show it to you again. The term conservative. The term conservative, right? Basically, when we're talking about a conservative field, it basically means that the path between the 2 points, if you move something along a path, a conservative field is independent of the path, right? So the curve or the thing that you're moving about it's not going to change your answer, right? So it doesn't matter which way you go from A to B, it's still going to give you the same answer. Okay, so you could even go, I don't know, you could even go like this. Maybe. Okay? So in these sort of questions, the information is captured by the value of the force, the vector field at the endpoints. That's it. Okay? And so to solve that, you apply this fundamental theorem, which depends on the endpoints of the curve or the line or whatever you're travelling across. And that's the equation that you're starting to solve. So you've got two partial differential equations there, and you want to come up with this scalar field, this function phi, that satisfies grad phi equals the given vector field. Okay? There's a little bit of an art form to do that. It's a little bit hit and miss, but essentially you do two integrations and then you compare the two things. Okay, so I'm comparing these. I've integrated that with respect to x. I've integrated that with respect to y. I get these things plus these constant sort of integration functions with respect to the other variable, and then you compare them. Okay? Once you've done that, happy days. It's just the fundamental theorem, which is the phi at the end point minus the phi at the start point. Okay? So I think I did this in a lecture last week, but it's a good example. It's a good example. Okay? So the phi should be, I'm pretty sure the phi should be unique there. Probably up to the phi is probably unique up to a constant. Yeah. So let me see if, okay, yeah, the phi is unique up to a constant, right? So if I put like a +1 here, would it still work? If you differentiate that, yeah, I could put any constant I like there. So, but I just choose the easiest one because I'm a simple guy, right? Questions? Oh, no. Okay. All right. Let's finish. I've got something to do after this, so there's something at the Opera House happening tonight that I'm going to, so I need to rush down there. But if people have questions, hang around, come and ask me. Good luck. Good luck with your test next week. Will I see you? I won't see you. I won't see you before the tests on Wednesdays. So do it, get 100%. I believe in you, and we'll see you next week.